Good evening. This is Math 2414. It's March 19th. Welcome back from spring break. I hope you had a good spring break, an enjoyable spring break. Maybe you got to do something a little bit different this past week instead of going to classes and doing homework and all that. Hopefully you also did some homework, especially calculus homework over spring break. We have a few announcements to make here as we get started with lecture. First of all, your next homework assignment that will be due will be April the 2nd. So I'm not going to assign any homework that's due this Sunday or the following Sunday. Next homework will be due April the 2nd. Exam 2. The review is posted on your Google site. And you have a very extensive review on your Google site, so please take advantage of that. Lots and lots of problems. The window for taking Exam 2 is March 22nd through the 27th. There will be a 3-hour time limit on that test. Make sure that you show up at a testing center with at least 3 hours before they close so that you have enough time to take the test. Will it take you 3 hours? For almost all of you, no, it shouldn't. You should finish it well under that. But you want to allow at least 3 hours just to give yourself enough time, that in case you run into something you have trouble with, you have a little bit of time to struggle on a problem and you can still finish the test. The test will cover integration techniques, about 50 points. About half the test is going to be integration techniques. When I say integration techniques, I'm talking about integration by parts, trig substitutions, trig integrals, powers of sine and cosine, powers of secant and tangent, using trig identities to evaluate integrals, and then also partial fraction decompositions, those techniques that we've talked about in this chapter. And then about 20 points of the test will be on L'Hopital's rule and improper integrals. And then about 30 points on parametric equations, which we kind of finished up what we were going to do with parametric equations last time. Now remember, there are some things that are not on this test that we cover with parametric equations that will be on Exam 3. So don't forget that arc length and surface area problems will be on Exam 3 from parametric equations. That will not be on this test. Again, look at your review to see exactly what this test is going to cover from parametric equations. Office hours this week. I will be online tomorrow, Tuesday, from 11 to noon, and then again Sunday evening from 8:30 to 9:30 p.m. I will be on campus this week. On Wednesday from 4 to 6 p.m. and on Thursday from 9:30 to 11:30 a.m. So take advantage of the on-campus hours. Don't forget that I am at the North Harris campus. And my office is Winship 115K. Winship 115K. Come by Winship 115 during those hours. Come by and ask questions. Be happy to help you out. I'll be more than happy to help you out. Today, our goal is to cover polar coordinates, the introduction to polar coordinates, graphs, tangents at the pole. I have a more detailed outline on the next screen. And then our next lecture, one last thing to mention here, next lecture is March the 28th. Remember, I will not be posting a lecture this Wednesday or next Monday because of me being on campus this Wednesday and because of the exam window next Monday. So this Wednesday and next Monday will not be posting any lectures. Next lecture gets posted March 28th. All right, so today it's all about polar coordinates. Very important, by the way, for those of you going on to take Cal 3. Very important. I can't emphasize to you enough how important this is in Cal 3. Very important in Cal 3. Because in Cal 3, first of all, you'll be using polar coordinates some, you'll be using parametric equations some, and also you'll be looking at cylindrical and spherical coordinates. Polar coordinates is a good lead-in to cylindrical and spherical coordinate systems. So it's important. This is a more detailed outline of what we're covering today. We're going to talk about, and I'm going to assume that you've seen polar coordinates before, but you've forgotten a lot of what you've seen. So that's my kind of motto with polar coordinates in Cal 2. that you've seen it before, you've got some familiarity with some very basic stuff, but you've probably forgotten a lot of things about polar coordinates also. So today we are going to talk about plotting points, literally being able to plot a point on a coordinate system, converting between polar and rectangular form and rectangular and polar form, graphing equations by plotting points, graphing polar equations by plotting points, symmetry, what it means to have a tangent line at the pole, and then classes of graphs that we'll talk about, and then finally talk a little bit at the end about calculating derivatives and looking at dy dx given a polar curve. All right, so that's what we're all about today. So let's get started. First of all, in rectangular form, you're talking about a rectangular coordinate system. You're talking about two axes, and everything's in relationship to these two axes. So when you've got a point in the plane, that point is specified by two coordinates, and those two coordinates, right, are given by the distance from the x-axis and the distance from the y-axis. Right, the distance from the x-axis b, that's the y-coordinate. The distance from the x-axis is the x-coordinate. And that's how we specify a location of a point in the rectangular coordinate system. In the polar coordinate system, instead of everything being related to two lines, the x and y axis, we have something called the pole, a point called the pole, and extending from that pole, we have something called the polar axis. And that polar axis kind of looks like the positive x-axis. The pole kind of looks like the origin, right? So this is the origin in rectangular form, and this is the positive x-axis in rectangular form that we're talking about. And a point's location in the plane is specified by two coordinates, just like in rectangular coordinates, but those two coordinates are the distance that that point is away from the pole, we specify that as r, and the angle that that point determines with the polar axis, the angle of rotation, theta. Theta can be measured both in degrees and in radians. You'll see it both ways. We're going to typically use radians. And so the location of that point in polar coordinates would be r theta, like that. Now, what's usually done at this spot is you go ahead and combine the rectangular coordinate system and the polar coordinate system on the same axes, right? And so then you have a point out in the plane that's specified in rectangular form as xy and is in polar form as r theta, like that. And we simply use the definitions of x and y and r and theta to come up with equations that relate the two coordinate systems to each other. All right, so if we take that point whose rectangular coordinates are x and y, then we know that this distance is x on our picture and this distance is y on our picture. And we also know that this angle here is theta, and we know that this distance is r. And so what we want to do is come up with some equations that relate x, y, and r and theta to each other so that we can do some conversions. So we're going to look at that. So right away, you see you've got the Pythagorean theorem that tells us that x squared plus y squared equals r squared. So we have that relationship, that it's always true that x squared plus y squared is equal to r squared. We also have that the tangent of theta is equal to y over x. So those are those two sets of equations right there that would allow you to relate polar and rectangular form to each other. And then we also have that the sine of, let's use cosine first, that the cosine of theta is x over r. It's adjacent over hypotenuse. And so that would give us a more useful form that x is equal to r cosine theta. And we also have that sine of theta is opposite over hypotenuse, so that'd be y over r. And so that would give us the more useful equation, y is equal to r sine theta. That's sometimes, these two equations together, the x equation and the y equation, are sometimes called the parametric form of polar coordinates, like that. So you have those two equations, and we have these two equations, and these are the transformation equations, and these allow you to actually go back and forth between polar coordinates and rectangular coordinates. Now, before we actually start converting between points, or converting points in rectangular form to polar form, and equations from rectangular to polar also, let's just talk about plotting points, first of all, and how that works. So let's just simply plot the point 3 pi over 4. 0.3 pi over 4. That's a point in polar form, right? So this is a polar point. Now, what you'll see frequently is you'll see polar graphing, where you've got concentric circles that would allow you to calculate or to plot the r values efficiently. I'm not going to do that. Instead, I'm just going to kind of hand draw one here. And what do we know? That every point on that circle right there is 1 unit from the pole. Every point on this circle, and pretend it's a circle, because it doesn't exactly look like a circle, but you get the idea, would be 2 units from the pole, right? So that would be r equals 2. Every point on this circle, and you get the idea, 3 units from the pole. And so on. And so that's my hand-drawn little polar paper right there. And so the 0.3 pi over 4, right, we rotate the polar axis counterclockwise, pi over 4 radians. And so there's theta equals pi over 4 right there. And then we simply count out 3 units on that line segment that starts at the pole, and we get the 0.3 pi over 4 right there. So there's 3 pi over 4. All right, so now let's look at another point. Let's plot 2 negative pi. 2 negative pi. So 2 says we're going to go out to 2 units from the pole. Negative pi, we are going to rotate clockwise because this angle is negative. So we're going to rotate the polar axis clockwise in this case. And so we actually go pi radians as our rotation this direction, clockwise, right? There's pi radians right there. And then we would march out 2 units, right? And here would be the 0.2 negative pi. Right, that's the 0.2 negative pi right there. Like so. All right. And so let's see. Let's look at the next point that I want to plot. Let's plot, let's say, 2 pi over 3. So, oops, not 2 pi over 3. Sorry. Let's say negative 2 pi over 3. That's better. All right, so first of all, we're rotating 2 pi over 3 radians from the polar axis. And 2 pi over 3 radians would be approximately, if I wanted to kind of hand draw that, might be like right about here, let's say. And that would be 2 pi over 3, theta equals 2 pi over 3, like that. That would be our rotation. And then, because the r value is negative, what we do is we extend that line segment back down into quadrant 4, like so, and then we count 2 units in that direction. And so this would be the point right here, negative 2 pi over 3. So notice that negative 2, 2 pi over 3 is a quadrant 4 point, like that. Also notice that if you plotted 2 negative pi over 3, the 2 negative pi over 3 is, let's see, so negative pi over 3 would be rotating back this direction like this. That would be negative pi over 3 like that. And 2 negative pi over 3, we'd march out 2 units. And notice that is the same point. And so 2 negative pi over 3 is the exact same point as negative 2, 2 pi over 3. So right away, one thing to observe here is that polar representations for points, polar representations for points are not unique. In fact, there's an infinite number of ways of writing out any point in polar coordinates and expressing it in polar coordinates. That's a significant difference between polar coordinates and rectangular coordinates. And rectangular representations are unique. Right, so rectangular representations for points are unique. So that's really different. And when I say are unique, that means that there's only one way to write it in rectangular form. Polar form, there's multiple ways of writing the same point. So as an example, we look at, let's do something relatively simple here. In polar coordinates, this point right here that I've just identified with a red dot right there has coordinates. One way to express that would be that it has coordinates of 2 pi over 2. Right, 2 pi over 2 describes that point in polar form. However, you could certainly have also done negative 2, negative pi over 2. That point also, or that representation also describes that point. Negative pi over 2 is a rotation that's clockwise, and then the r value is negative, so you go back in the opposite direction. Also, certainly notice that not only is 2 pi over 2, but 2, if you add 2 pi to that, 2 5 pi over 2 is also a representation for that point. In fact, notice that if you take 2 and you take pi over 2 and you add or subtract any multiple of 2 pi, 2n pi, and add or subtract to pi over 2, you're going to get another representation for that point, right? And so on. So all of these ways that I've written right here are all ways of describing that one point in polar coordinates. So that's a really, really different aspect of polar representations for points than you see in rectangular form. All right, so now what we want to do is we want to look at converting equations between polar form and rectangular form, going back and forth. It's one thing that I would like you to be able to do is take an equation and convert it from rectangular form to polar form. So we're going to go ahead and look at, well, let's actually do conversions with points first. That's one thing I meant to do. So let's see, converting points from polar to rectangular. And I'm going to put a double-ended arrow there because we want to go both directions here. All right, so let's say that we have the point 1, 1. Right, the point, and that's in rectangular form. And I want to convert that to polar form. Right, so I want to convert to polar form. So if we do it this way, we know that x squared plus y squared is equal to r squared. X and y are both 1 here, so that'd be 1 plus 1 equals r squared. So r squared would be equal to 2. So r would be equal to, and r would technically be equal to plus or minus the square root of 2. right? And it could be that we're going to use positive square root of 2. It could be that we're going to use negative square root of 2. Right? Well, it depends on how we're going to write this. All right, and then we want to find theta. So we have the tangent of theta is equal to y over x. So tangent of theta is equal to 1 over 1, or 1. And so theta would be equal to the smallest angle, or that smallest positive angle where we would use it, where we'd have that would be at pi over 4. So in polar form here, this point, the easiest way to write this would be to use positive square root of 2, and then use pi over 4 for the theta value. And so that would be the polar form for that point. Let's go ahead and move this up right here. So it takes up a little less room in the page. Okay. All right, so let's look at the point negative 3, 4. I want to take that point and convert it to polar form. All right, and let's go ahead and use positive r values here just to make our lives a little bit easier. Okay, so we have r squared is equal to x squared plus y squared. So r squared would be equal to 9 plus 16. R squared would be equal to 25. R would be 5. We could also use negative 5 and get a representation for negative 5 if we wanted to. Okay, then we know that the tangent of theta is y over x. So in this case, tangent of theta excuse me, is equal to 4 over negative 3. And so in this case, theta would be negative 4/3. I'm sorry, not negative 4/3. Whoops. The arctangent of negative 4/3, that's better. So the arctangent of negative, and actually probably the easiest way to do this would be, instead of using negative 4/3 there, we'll use the negative of arctangent of 4/3 like that. So arctangent of 4/3, 4/3 would be a positive value there. We're going to get we're going to get theta to be approximately, if you use a calculator here, it's going to be approximately equal to 2.21. So what we want to use a quadrant 2 angle here. Note, right? We need a quadrant 2 angle because negative 3, 4, this point is in quadrant 2, right? It's in quadrant 2, and so we need a quadrant 2 angle. And so the quadrant 2 angle we could use using our calculator would be approximately 2.21. All right, what I would do is I would just take the arctangent of 4/3. That gives me a quadrant 1 angle, and then use that as the reference angle for my quadrant 2 angle. Right, and so that's usually the route I would take here. So the arctangent of 4/3, just to put a little bit more detail in there then. Let's see, so I'm using my calculator here. So okay, so we're going to use arctangent of 4 divided by 3, and that gives me 0.927. So if you've forgotten how to do this, so I just found the arctangent of 4/3, which is 0.927 approximately. That forms the reference angle for the angle we're trying to use in quadrant 2. So right, that's 0.927 right there, that angle. And so the angle we're after is this one right here. And so what do? We take pi minus 0.927. So when I take pi minus 0.927, I get the 2.21 that I just wrote down a minute ago. So that's approximately 2.21. So that's how I got the 2.21 there. And that may have been a while since you've done that. Notice you did have to be concerned about what quadrant you were in for this particular point in order to choose the right angle for the point that you have. So it's something that you just need to watch for. All right, let's see. Let's look at one more conversion like this, and then we'll convert the other direction. So let's say we have the point 5 square root of 3, negative 5, and I want to convert that one into polar form. Okay, so I have that r squared is equal to x squared plus y squared. By the way, 5 square root of 3, negative 5 is in quadrant 4. So be thinking about the fact that you've got to use a quadrant 4 angle in this problem, right? We need to be over here somewhere. Right, so I'm going to need a quadrant 4 angle, and let's use positive angles here. So that's the angle I want to use, the smallest positive angle. Okay, so we get r squared is equal to 5 square root of 3 squared plus negative 5 squared. And so that would be r squared would be equal to 75 plus 25. R squared would be 100. R would be 10. Again, technically plus or minus 10, but we want to use, since we're going to use the smallest positive angle like this, we're going to use positive 10 for R. All right, tangent of theta. What do we got here? We've got that it is y over x, so this would be negative 5 over 5 square root of 3. And so you get tangent of theta is equal to negative 1 over the square root of 3. If you rationalize that, you get tangent of theta to be negative square root of 3 over 3. All right, so that's going to give you an angle in quadrant 4. And again, the reference angle, think about where the tangent of theta is equal to positive square root of 3 over 3. Tangent of theta is equal to positive square root of 3 over 3. That's actually a special angle, and that's when theta is equal to pi over 6. So the quadrant 4 angle that we'd be using, right? This is quadrant 4 right here that we want to get. And so this is going to be you could use negative pi over 6 if you wanted to, but I said to use the smallest positive angle here. So I'm going to use 11 pi over 6. Okay, and so the point that I've got here is going to be, the point in polar coordinates is going to be 10, 11 pi over 6. If you had removed the restriction of using the smallest positive angle, you could have used 10 negative pi over 6. That would have been fine too, but I was using the smallest positive angle that I could here. All right, so now let's go in the opposite direction. Let's look at some points that are in polar form, and let's convert them to rectangular form. So let's say I have the point 3 pi over 3, and I'm going to convert that to rectangular form. This is probably less decisions to be made when you're going in this direction. You're simply going to use our parametric forms for conversion. So x equals r cosine theta, and y is equal to r sine theta. So in this case, we have that r is 3, theta is pi over 3, so this would be 3 cosine of pi over 3. Y would be 3 sine of pi over 3. Right? Cosine of pi over 3 is 1/2, so this would be 3 times 1/2, or 3/2. And sine of pi over 3 is the square root of 3 over 2. And so you get 3 square root of 3 over 2. All right, and so that would be our rectangular form here, would be the point 3/2, 3 square root of 3, 2, like that. Like I said, this is not as difficult, probably going to rectangular form here. Not as many decisions to make, I guess. All right, let's look at one more like that, and then we're done with this aspect. So let's say we've got the point 6, negative 5 pi over 6. And again, I want to convert that to rectangular form. So I have x is equal to r, which would be 6, cosine of negative 5 pi over 6. And y would be 6 times the sine of negative 5 pi over 6. Now, negative 5 pi over 6 is a quadrant 3 angle, right? And so the sine and the cosine are both going to be negative in this case, right? And then again, you're just worried about what the cosine of pi over 6 is, right? You know that the cosine of pi over 6 is the square root of 3 over 2. And you know that the sine of pi over 6 is 1/2. So in this case, they're going to both be negative because it's a quadrant 3 angle. So this would be 6 times negative square root of 3 over 2. And for y, you'd have 6 times negative 1/2. And so you get negative 3 square root of 3 for x, and for y, you get negative 3. And so that's our point. Right, negative 3 square root of 3, negative 3. Okay. So that's how we've plotted points now. We've converted. And so now let's look at taking some equations and actually converting them from one system to the other. All right, so let's take this equation. Polar equations are frequently written, remember, in the form, not always, but frequently written in the form r equals a function of theta. That's the most common form for polar equations. So I'll say this is the most common form. Not the only form, definitely, but the most common form. Okay, so let's take this polar equation, r equals 4 sine theta, and let's go ahead and convert that to rectangular form. In other words, let's rewrite this equation with just x's and y's in it. Okay, so you have r equals 4 sine theta. So one way that you could deal with this is you could multiply both sides of this equation by r. There's several ways you can make the conversion here. This is one way. And so this gives you r squared equals 4r sine theta. Okay, and so what do we have here? We know that x squared plus y squared is equal to r squared. And we also know that y is equal to r sine theta. So notice those two equations you can plug in here, and you get x squared plus y squared in place of r squared equals 4, and then r sine theta would be y. And boom, you've got the equation in rectangular form. Okay, and you could complete the square here if you wanted to identify the graph. You have x squared plus y squared minus 4y equals 0. So x squared plus y squared minus 4y plus 4, right? Add 4 to the y's to complete the square in y. Add 4 to the other side of the equation also. And you have x squared plus y minus 2 squared equals 4. And I don't know if you remember what this graph is, but this is a circle. This is a circle with a center at 0, 2 with a radius 4. Like so. And so that tells you the graph of r equals 4 sine theta. That r equals 4 sine theta is a circle centered at 0, 2 with a radius of I'm sorry, I said a radius of 4, but that should be a radius of 2. That's better. Radius of 2. Okay, so it's an interesting thing that's going on there. So let's go ahead look at the next problem. Let's say we've got just this equation. Notice this is not in our common form, just theta equals pi over 3, and I want to convert this to rectangular form. Okay, so if we go ahead and take the tangent of both sides of the equation, we get tangent of theta is equal to the tangent of pi over 3. And so we get tangent of theta is equal to square root of 3. But then what else do we know? We know that tangent of theta is equal to y over x. And so you can substitute that in here for tangent theta, and you get y over x is equal to square root of 3. And you get y equals the square root of 3 times x. That graph is a line through the origin. Graph is a line through the origin, through 0, 0. Okay, so this was our polar equation. This is the corresponding rectangular equation, y equals the square root of 3 times x. Notice you have to kind of, in some cases, be a little bit ingenious about how you go about these types of conversions. So, all right, let's look at one more like this. Let's look at this equation. Let's say we have r is equal to 6 cosine theta minus 8 sine theta. Okay, and I want to go ahead and convert that one into rectangular form. To see what the graph might be. Okay, so in rectangular form here, let's see, we want to get this all in terms of, remember, the idea is to try to get this all in terms of x's and y's, right? So we've got our conversion equations, and so let's see if we can use those conversion equations here. So if we multiply both sides by r, we used that trick once before. Let's see what that does for us in this problem. So I'm multiplying both sides by r. One advantage that gives you is that you give it an r squared in there. So that's always nice. And then you have 6r cosine theta minus 8r sine theta. And then r squared is x squared plus y squared. And then remember that r cosine theta is x, so that'd be 6x. And then r sine theta would be y, so this would be minus 8y. And boom, you've got the equation in rectangular form. And then we could go ahead and complete the square to actually see what this graph looks like. Complete the square in both x and y. And let me change this. This should be minus 6x right here. So it's x squared minus 6x, leave a space, and then y squared plus 8y, leave a space, equals 0. For x's, to complete the square in x's, I'd add 9. For y squares, for the y's, to complete the square, I'd add 16. We have 9 plus 16 on this side. So this gives you x minus 3 squared plus y plus 4 squared equals 25. This is a circle. The center is at 3, negative 4. The radius is 5. By the way, notice that since the as far as the graph goes, notice how this works out. Well, let me put the x-axis a little bit nicer than I just did. Okay, so 3, negative 4 is sitting like right here. And then the radius is 5. And what I want you to notice is because x and y are 3 and 4 there, that this means that this distance right here is 5. And so this circle is actually a circle that goes through the pole. Use a little bit of symmetry here to graph this circle. And so you get a circle that kind of looks like this. It actually passes through the pole. I'm not going to draw the whole thing, but you get the idea. Right, so this is a circle through the pole. And remember what the equation looks like at the beginning. All right, so let's now go the other direction. Let's take an equation that's in rectangular form and convert it to polar form. So let's say we have x squared minus y squared equals 16. I want to convert this to polar form. So remember, we know that x is r cosine theta and y is r sine theta. So you could write this as x squared would be r squared cosine squared. So you have r squared cosine squared theta minus r squared sine squared theta equals 16. You could factor out an r squared, and you get cosine squared theta minus sine squared theta. And I don't know if you remember this, but the double angle for the cosine, that's an identity in trigonometry. So the double angle identity says that the cosine of 2 theta is cosine squared theta minus sine squared theta. And so this would give us r squared is equal to r squared cosine of 2 theta is equal to 16. Or if you wanted to move it to the other side of the equation, you could say r squared is equal to 16 secant of 2 theta. Because you'd be dividing both sides by cosine of 2 theta there. I wouldn't take the square root. I would just leave it like that. R squared equals 16 secant of 2 theta. Okay. And let's look at one more. Let's look at the equation x equals 8. Let's convert this to polar form. So again, you know that x is equal to r cosine theta. So notice right here we just have r cosine theta is equal to 8. Divide both sides by cosine, and you get r is equal to 8 secant theta. 8 over cosine, which is 8 secant theta. And that's the polar form right there. Right, pretty quickly arrive at that form. Okay, so we've plotted points. We know how to do that. We've converted between polar equations and rectangular and vice versa, both points and equations. And so now let's go ahead and actually look at a graph and plot a graph by plotting points. So let's say we have this equation, r is equal to, let's say, 4 plus 2 sine theta. And I'm going to change that. Let's make it cosine theta. Now what you could do here to graph this, you could just plot points here, right? And you'd have an r value for a corresponding theta value. Right, so when theta is 0, cosine of 0 is 1, so r would be 6. When theta is pi over 2, cosine is 0. Cosine of pi over 2 is 0. So 2 times 0 would be 0, r would be 4. When theta is pi, cosine of pi is negative 1, so you have 4 plus negative 2, which is 2. 3 pi over 2, once again cosine is 0, so you get 4 again, and 2 pi clearly would give you 6 again, right? Because cosine of 0, cosine of 2 pi, you get the same values. So let's see if we can kind of piece some things together here on this graph. So you have 6, 0. Is out here. There's 6, 0. And then you have 4 pi over 2. So 4 pi over 2 would be this point right here. You have 2 pi. So rotation of pi, you get 2 like that. And then you clearly have some what looks like symmetry here. You know, and so you get these points right here. You could certainly go ahead and fill in more details if you wanted to. Like you could look at what's going on possibly at pi over 2. I'm sorry, pi over 4, or pi over 6. You know, use special angles to your advantage on problems like this. What you'll come up with here is that this graph, as you fill in more detail, it's kind of a graph that has what looks like kind of a flat side to it, like this. And sometimes that flat side may actually have an indentation in it, possibly. This kind of graph is actually called a limacon. I do want you to be able to identify some major classes of graphs. We'll talk about those in a minute. There's a couple of other things I want to talk about in the next problem also. But certainly you can also use graphing technology to your advantage. So the problem we're graphing is 4 plus 2 cosine theta. So you know, using a grapher of some type, we could use polar form. So in this case, I'm using looking at a polar equation where we have r is equal to 4 plus 2 cosine theta, like this. And notice this is from negative pi to pi as far as the setup on this particular app. Most commonly, you'll see it from 0 to 2 pi. And here we have our graph. And notice the graph, if we kind of zoom in here a little bit, notice there is a flat side to this graph, right? And we're going to talk about how you can tell when you've got a flat side like this. All right, this is an example of a limacon. All right. If we just change this a little bit, let's say we have r is equal to not 4 plus 2 cosine theta, but let's say we have 2 plus 2 cosine theta. Like this, plot these points. Even if you're using a graphing calculator, I think being able to plot some points like this is instructive. It gets you used to using polar coordinates again. I think that's a good thing. So we'll do 0, pi over 2, pi, 3 pi over 2, 2 pi, just like you did in the last problem. So when theta is 0, you get 4. When theta is pi over 2, you get 2. When theta is pi, if cosine of pi is -1, so you have 2 plus -2, that's 0. So remember, when r is 0, you're at the pole. 3 pi over 2, you'd be at 2 again, and at 2 pi, you'd be at 4 again. So that graph somewhat different. You've got 4 here. When r is 0, and then when theta is 0. When theta is pi over 2, r would be 2. When theta is pi, r is 0. So you're at the pole. And then you get 2 again when theta is 3 pi over 2. And finally, you're back at the point 4, 2 pi. This graph kind of looks like this. R comes in towards 0 and actually comes into the pole right there. And this is actually called, this type of graph is called a cardioid because it kind of has a heart sort of shape to it. All right, so this is an example of what we call a cardioid. All right, now let's look at changing those two constants, similar kind of equation, but now let's say we've got 2 plus 4 cosine theta. 2 plus 4 cosine theta. All right, so we make our little chart, our little t-table, our little polar t-table. We'll use 0, pi over 2, pi, 3 pi over 2, 2 pi. When theta is 0, you get 6. When theta is pi over 2, you get 0. When theta is pi, and this is where it gets interesting, when theta is pi, you have cosine of pi is -1, you get -2. And at 3 pi over 2, you're back at 0. And at 2 pi, you are at 6 again. All right, so what the heck is happening here? Well, what's happening is, let's see, this graph is over here at 6, 0, right here. And then at pi over 2, R is 2. I think I missed that here, and I apologize. R is 2. That's better. And so let's change that. I was not paying attention there. And some of you may have been pointing that out to yourselves as you're going through there and going up. I think he's screwing up here. When theta is pi over 2, cosine of pi over 2 is 0, so R would be 2. That's better. At pi, that it is negative 2. That's correct. And at 3 pi over 2, you're at 2 again. Okay, so much better. All right, so now at pi over 2, you're at 2. That's better. And at pi, you're at negative 2. Negative 2 pi is this point right here. This is the point negative 2 pi right here. So what I want you to see is that this graph is coming in like this. And then to get from that point to the point negative 2 pi, to get from the point 2 pi over 2 to negative 2 pi, the graph has got to go through the pole somehow. And when it goes through the pole, what we get right here is what we call a tangent at the pole. So the graph passes through the pole. The graph passes through the pole. That's the only way it can get from a positive R value to a negative R value. And it passes through the pole along a tangent at the pole. And how do you find that tangent at the pole? You set R equal to 0 to do that. And you get this equation, 0 equals 2 plus 4 cosine theta. You get negative 2 equals 4 cosine theta. Negative 1/2 equals cosine theta. And you get theta is the arc cosine of negative 1/2 here. And you've got this angle in quadrant 2. You know that the cosine is equal to positive 1/2 at pi over 3. And so this would be at 2 pi over 3 right here. So 2 pi over 3 is this angle, maybe that looks like this through the pole. That's theta equals 2 pi over 3. And that acts as a tangent at the pole. And so what happens is this graph actually comes in and skims off that angle at 2 pi over 3, passes through the pole there, and it comes back to this point like this. And there's going to be an equivalent tangent at the pole over here at 4 pi over 3 down here. And so what happens is this graph is going to have symmetry here. We're going to talk more about symmetry in a second. And this graph passes, well, through that angle also, and then comes back around towards our original point. Here at the point 6, 0. This is sometimes called a limacon with an inner loop. All right, and so definitely a major class of graph and a good illustration of where tangents at the pole come in handy. That you needed that tangent at the pole to see at what angle this graph skimmed through the pole at. Okay, and not a bad one to look at on a calculator also to probably have a little bit better of a graph than I just sketched. So notice this one is, what was it? It was 2 plus 4 cosine theta. And notice you get this tangent, this graph that actually passes through the pole, and the angle that it passes through that pole at is called the tangent at the pole. Right? And this is called a limacon with an inner loop. Okay. So now let's go ahead and go on and let's see, we've plotted some points to look at some graphs. We've talked about tangents at the pole. We talk about symmetry here. To kind of finish this off, notice that these last couple of graphs have all had symmetry with respect to the x-axis. One thing that's nice to know is that if r is a function of cosine of theta, all you have are cosines, then you have symmetry with respect to the x-axis. If r is a function of sine of theta only, then you have symmetry with respect to the y-axis. Okay, so always nice to know that going into a problem. Okay, so if we have this equation right here, if we have r is equal to 1 minus sine theta, because of the nature of the equation, because this is just r as a function of sine theta only, I know that this graph has symmetry with respect to the y-axis. Very helpful when you're sketching the graph. So you could go through and plot a few points if you wanted to. Use the fact that you've got this symmetry with respect to the y-axis. When theta is 0, r would be 1. When theta is pi over 2, r would be 0. When theta is pi, r would be 1 again. When theta is 3 pi over 2, r would be 2. And then you'd be back to 1 again. This graph kind of looks like this. You have a piece that looks like this, and then you have a symmetric piece. On this side, this is a cardioid that has symmetry with respect to the y-axis. Okay, so like I said, there are a bunch of graphs that I want you to know what those look like. And so let's write those out here. Let's make sure that these are in the notes. We have, first of all, lines through the pole. Equations that are lines through the pole always have equations in the form theta is equal to a constant. A circle through the pole always has an equation, or is an equation that looks like this. R equals A cosine theta plus B sine theta. We graphed one like this or we looked at one a few minutes ago like this, where we converted from one form to the other to actually show that you had a circle through the pole. A circle around the pole is just r equals a constant. Right, so one's a circle through the pole, the other one's a circle around the pole. A linear spiral is an equation that looks like this. R is equal to A plus B theta. No trig functions involved there at all. Cardioid, we've talked about this kind of graph already now. Our equations in the form r equals a times 1 plus or minus cosine theta, or r is equal to a times 1 plus or minus sine theta. And sometimes you'll see that written as just a plus or minus a cosine theta, or a plus or minus sine theta, like so. Right, those are cardioids. Limacons. Limacons, sometimes you'll see it referred to that way. Our equations in this form: r is equal to a plus or minus b cosine theta, and r is equal to a plus or minus b sine theta. If the absolute value of b is greater than or equal to the absolute value of a, b is bigger than a, in other words, then you have an inner loop. We looked at an example like that on the last screen. If that constant in front of the sine of the cosine is bigger than the a value, then you're going to get an inner loop on the graph. And then finally, the last category that's important are the roses. R is equal to a sine of b theta, and r is equal to a cosine of b theta. These are what we call rose curves. And the number of petals has to do with the b value. If b is even, then you have 2b petals. In other words, you have twice as many petals or leaves as you do that constant. And if b is odd, then you have exactly b petals. And when I say petals, you could say leaves if you want to. That'd be okay. A tells you the length of each leaf. So, for example, here, if we have r is equal to 2 cosine of 3 theta. Think about the things that you know right away about this graph. First of all, you know it's a rose because of the form that it's written in. Because the b value is 3, you know that there are 3 petals. Because it's r is a function of of cosine of theta only. You just have cosines over there. You have symmetry with respect to the x-axis. And then finally, that 2 in the front tells you the length of each leaf. So you get lots of information. Just based on all those different constants here. So you have this 3-leaf rose. And so you can think about plotting points if you wanted to. But once you get the graph started, you know, if you think about where the ends of the leaves are going to be, I want you to think about how you get the ends of the leaves. You get the ends of the leaves when the cosine of 3 theta is equal to plus or minus 1, right? Because that's as big as you're going to get the r value to be. The biggest you're going to get the absolute value of the r value to be. So where is the cosine equal to positive or negative 1? Well, it's equal to positive or negative 1 at 0, and at pi, and at 2 pi, and at 3 pi, and so on, like this, right? Multiples of pi. So theta would be equal to 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, and so on, like this. Right? And this gives you an idea of where the ends of these leaves are going to be. So you've got pi over 3, let's say, is this angle like this. Right? 2 pi over 3 maybe looks like this. 4 pi over 3, 5 pi over 3, and so on. So if this is pi over 3 right here, if you think about the fact that, and then obviously you also get 0 and pi like this. So if that's 1 and 2 on the x-axis there, then r starts out at 0, or theta starts out at 0, r is going to be 2. So you're starting out at this point out here like this. And what's going to happen is the graph's going to come in towards the pole. You could even look at tangents at the pole if you wanted to get an idea. But the ends of the leaves are going to be out on these axes like this. And the graph is going to have ends of the leaves are going to be out here. Let's see, 1, 2, out like this. This graph's going to come in like this, come out. Notice that there's going to be tangents at the pole here. You could have calculated the tangents at the pole to see how the graph comes in towards the, through the pole there, to look at those tangents like that. Notice that there's going to be a tangent at the pole right here, and clearly looks like it's going to be less than pi over 3, right? You're going to have that, and so you could calculate the tangents at the pole. Tangents at the pole, remember you said r is equal to 0, and so if r is 0, you get 0 equals 2 cosine of 3 theta. So you get cosine of 3 theta is equal to 0. So 3 theta, where's cosine 0? At pi over 2, at 3 pi over 2, and so on. Divide by 3, you get theta is pi over 6. So notice that's what where this one is right here. You get pi over 2, and so on. Right, and you can see where it's pi over 6 and pi over 2 come into play. Here's our tangent at the pole at pi over 6. Right, so the graph comes around, and then when it comes back through the pole, you've got this tangent at the pole right here at pi over 2 like this. Right, and the graph is going to kind of circle back through and skim off of that line. So you have a lot of different tangents at the pole for this graph. All right, so what we're going to do now is we're going to finally finish here by looking at trying to calculate dy dx. Calculate the derivatives here. So let's say we have this function. It's always nice to kind of start off with a cardioid to look at these kinds of problems. So let's say we have this cardioid, r equals 1 plus cosine theta. You can make a quick sketch of this cardioid. When theta is 0, r is 2. When theta is pi over 2, r is 1. When theta is pi, r is 0. You have symmetry with respect to the x-axis because this is a function of cosine only, right? So you're going to get a cardioid that kind of looks like this. All right, so let's find dy dx here. Let's find the slopes of the tangent lines. So remember that if you've got y is a function of theta, and x is another function of theta. If we have x and y expressed parametrically, then remember that dy dx is dy d theta divided by dx d theta. Okay, so we can actually take advantage of that in this problem because we know that x is equal to r cosine theta and y is equal to r sine theta. And what's r in our problem? Well, r is 1 plus cosine theta. So we've got that x is equal to 1 plus cosine theta times cosine theta, and y is equal to 1 plus cosine theta times sine theta. And we can actually find dy dx this way. So dy dx would be dy d theta divided by dx d theta. Then you simply use the product rule for both of those. You can multiply them out too if you wanted to, but you're going to have to use the product rule one way or another. So you've got dy d theta would be the first, 1 plus cosine theta, times the derivative of the second, which is cosine theta, plus the second times the derivative of the first, and the derivative of the first would be negative sine theta, derivative of 1 plus cosine theta. Like so. And then the denominator, what do we have? We have first times the derivative of the second. This is dx d theta. So it'd be 1 plus cosine theta times negative sine theta, plus the second times the derivative of the first. Derivative of the first is still negative sine theta, and this would be times cosine theta, like that. All right, and so you could kind of simplify this. You've got cosine theta plus cosine squared theta minus sine squared theta. That's our numerator. In our denominator, you get negative sine theta minus sine cosine theta minus sine cosine. So you get cosine theta. You know, it depends on what you want to do with this, is how much you simplify it. But this is cosine squared minus sine squared. Please don't say that that's 1, because remember, that's cosine squared plus sine squared. In the denominator, you get negative sine theta, and then this would be minus 2 sine theta cosine theta. And so notice you actually get two double angle identities. Whether you want to use those or not depends on, again, on the problem, but on the numerator, you could write this as cosine theta plus cosine of 2 theta. And in the denominator, this would be negative sine theta minus sine of 2 theta. And so that would be dy dx. That's the slope of a tangent line for any theta value here. So, you know, one thing we're going to be talking about next time is looking at horizontal and vertical tangents. So you can see that this problem, this graph has several vertical tangents, right? Several points where there's going to be vertical tangents and several points where there's going to be horizontal tangents. And we could just be looking at slopes of tangent lines also. Just to kind of finish this example, this is theta equals pi over 6, like this. We're talking about this point, and it looks like the slope of the tangent line there should be negative, right? So if we actually evaluated dy dx at theta equals pi over 6, we should be getting the slope of that tangent line. So this would be the cosine of pi over 6 plus the cosine of pi over 3 divided by negative sine of pi over 6 minus the sine of pi over 3. So cosine of pi over 6 is the square root of 3 over 2. Cosine of pi over 3 is 1/2. In the denominator, the sine of pi over 6 is 1/2, so that's negative 1/2. Sine of pi over 3 is negative square root of 3 over 2. Like so. And by the way, notice what you get there is you get, if you look at this, in the numerator you have square root of 3 over 2 plus 1/2, and in the denominator you factor out a negative 1, you get negative square root of 3 over 2 plus 1/2, like that. You end up with negative 1 as the answer. That's the slope of the tangent line at that point, which is not far off from the way I got sketched. I know I kind of didn't do a great job of sketching that one, but it certainly makes sense with the graph that I've got. Okay, so what we have done is we have talked about and gone through section 7.3 in your textbook, and we have actually started in on section 7.4 and started talking a little bit about derivatives. So next time what we will do, so this is March 28th. Let me flip the screen here. On March 28th, will all be about calculus and polar coordinates. In particular, we'll be looking at areas and lengths. And also horizontal and vertical tangent lines. Okay, so that's what we'll be talking about on March the 28th. All right, so that finishes up our lecture for the day today. Remember that you've got exam 2 this week. I have office hours tomorrow, on Tuesday, and again on Sunday. There's a great review online. Please be working on that review. Have a great week. Let me know how I can help. Remember, I'll be on campus on Wednesday and Thursday of this week from 4 to 6 p.m. and on Wednesday at 9:30 to 11:30 Thursday morning. Have a great evening. Have a great week. And hopefully I'll be talking to you soon.